Hi everyone and welcome back to your channel FE Civil Exam with Farhad. In this mechanics of materials. In this example, we want to solve a maximum deflection for a cantilever non-prismatic beam with a concentrated load of P at its free end. So by non-prismatic, we mean that a beam with a changing cross section. So for example, it has like a height of h naught at the beginning and it just goes it decreases and all the way through the end of the beam, like where the pressure applies force applies there, it just reaches to a very thinner thickness. So we want to calculate the delta maximum, which is the delta at the free end. So if we draw the deflection of the beam, which is the delta at the free end, which is A, and that's equal to delta maximum. And considering the non-prismatic concept of the beam, for non-prismatic beam, we have like the other name of non-prismatic is a constant strength. So that says the sigma or stress in any cross section is equal to m over s. Definitely m is changing from the beginning to end, and section modulus capital S, which is I over C, that's also changing because I is a function of x, and then the C, which is the x itself, is changing. So S is changing, M is changing, and M is simply P times X. X is changing, for example, from the free end. If you consider this is the origin, this is length of X, so the moment is changing. So they design the beam in such way that the stress or strength of the beam remains the same by playing with these two components. And the other consideration is that with the second theorem of moment area method, we can calculate the maximum deflection. So if you consider m over ei and then applying the second theorem of moment area method, so that says delta maximum, which is delta A, is equal to tangential deviation of A. So this is tangential deviation of A from a horizontal line at B, mhm, which is which stands for this distance. That's exactly delta A, and that's delta maximum. And how we calculate the tangential deviation of A with respect to B, that's the, if we just consider an element with the length of dx and standing at the distance of x from the vertical line which passes through A, so that's TA with respect to B is the integration of over the length of the beam from A to B, or from 0 to L, x times mx over ei, which is a function of x dx. How we can solve that? So for non-prismatic beam, delta maximum, it comes from this equation, which is the just extracted from the second moment, is applying of second moment area theorem method. So we can easily see Ix is changing, Mx is changing as well, but that's simple. That's P times X. But we have to calculate Ix. Ix is 1/12 base cube height, but height is a function of X as well. Height of the section. I mean, if you create a cross section at any instant of the beam, you can have a rectangular cross section, and but that's based of the distance of x, that's a function of x. So if we can get a relation of hx, a function for hx, then we can calculate the moment of inertia of I as a function of x. So the first assumption of our case was that the non-prismatic beam are designed in such way that they are constant in a strength, or that's equal to sigma allowable. That's moment over section modulus. And that says if we cut the beam through by the length of x and calculate the moment there, that's mx, that's p times x, and then sigma for that cross section, that's mx times hx over 2, mhm, is equal to over ix. This hx is like simply I over c, and c is h over 2. That goes up for, and the numerator, and it should be equal to the same strength at the very beginning of the support. That's m times h over 2. That's half of the height of the beginning over I naught. And if you and simply you can easily see at the all the way through the support, the moment created is p times l, length of the beam, and here is p times x. I naught is 112 base cube height, but that's h naught cube, and ix is 112 base cube height, but that's h of as a function of x. If you simplify this equation, then you will get a parametric equation of h of x as a function of x, that's a square root of x over L times h naught, which is the height at the support. As soon as we have this part, we can easily replace this parametric equation in the h uh, equation and then calculate the I as a function of x. So hx is equal to a square root of x over L times h naught, and ix is this equation. I naught is 112 base h naught cube, and if we just divide these two equations, we can get ix, which is comes from this equation. And as soon as we have ix, we can replace that in our delta maximum or second moment area theorem to get the delta maximum. So if you replace Ix in the delta equation, and delta maximum is tangential deviation of A with respect to horizontal line from B, and if you just replace it, it just gives you this integration. If you integrate it, it just gives you delta a to b. You can replace it by the limit of 0 to L PL to the power of 1 and half EI naught x to the power of 1 half dx. And then it just gives you the delta maximum is 2/3 of PL cubed over EI naught. And the interesting part is when you make a comparison with prismatic beam with the same loading, with the same support condition in comparison versus to a non-prismatic beam, delta maximum for this beam is a PL cubed over 3 EI. We can easily find that in the reference books. And this one we calculated that for a non-prismatic, that's 2 PL cubed over 3 EI. And then the takeaway note is the maximum deflection in an in a non-prismatic beam is as twice as the prismatic beam with the same loading materials and support conditions. And that also makes sense because it just, if this is both of them, just assume these two are H naught, assume the thickness remains H naught, and this is H naught and just varies to the other end of the beam. So we can simply expect that this beam, by effect of the same loading, has a more downward movement delta maximum in comparison to the complete rectangular one. So this is delta maximum. So this is more solid in a kind of some sense. Thank you. And this is mainly not kind of a PE exam question. This is more kind of P and SE question because it's more kind of conceptual, but it's good to deal with such problem in terms of structural analysis, understanding, mechanics of materials, understanding of beams. Thank you.